Well, in a number of respects, now for something completely different. First, let me congratulate you all on contributing to for me, a wonderful couple of days, a wonderful conference. I think the originator, the instigator of the conference, Don Sari, deserves a big hand.
Lewis
and he had very able conspirators in Lewis and Jennifer, and I'd like to thank you very much. I've heard some really outstanding talks over the last couple of days. I'm not going to try to summarize them and put them together. Some are clearly in the mode of injecting ideas that originated historically in quantum mechanics into cognitive psychology. And those efforts are the ones that I want to focus on. In particular, yesterday we heard from one of the most original minds in this whole enterprise, namely Jerome Bussmayer. And I congratulate him. He has, very seriously, he has injected a new life, a new interest, for me at least, into a wide range of topics in cognitive psychology, and there is, if you look at things in the right way, there really is a sense that wasn't there before of a kind of underlying unity. And that's an enormous achievement, and I'm really delighted to see this. It's given me a new interest in areas that appeared somewhat fragmented, somewhat stale, for lack of a better expression, and to see a unity of modeling and descriptive ideas that bring these different parts of our field together is a great achievement. And so, what can I say? Well, the way I tend to operate is to take a concrete example of a good idea and to work it through, looking for ways to generalize rather than the other way around. And some people tend to develop very general ideas and then look for concrete, specific applications. As I said before, I tend to do the opposite. I like to look at concrete features of a theory. Is the theory yet mature? If it has weaknesses, can those weaknesses be eliminated or at least ameliorated? So let me attempt to do that with work that we heard yesterday from, in particular, Jerry and from Jennifer. And I want to remind you of this decision-making experiment that was carried out by Jennifer. And it consists of asking people to make subjective probability judgment or judgments of ratings that can be converted to probabilities in a straightforward way. And there are a whole bunch of cases, some of which you saw concretely yesterday. And altogether, there are 13 numerical probabilities that need to be accounted for. There is an initial judgment before a case is heard, before any evidence is given relevant to that case, an initial judgment of guilt. And the interesting fun and games begin with the presentation either of a prosecution's case, a defense case, and there are two levels of strength, which are denoted weak and strong in each case. Following the initial presentation, there is a second probability judgment. So there's one here, there's one here, and there is one at the end. And by the end, I mean a subject follows a single path. This particular subject hears a weak prosecution case followed by, let's say, a weak defense. Or another subject may hear the same weak prosecution case followed by a strong defense. So the probability judgments you can expect to change, and they do. So I have a number of questions. And some of these you might be able to answer. Others you might want to think about. The first question I have is, the reported data are 12 probabilities, or 12 numbers that represent probabilities. But that's not the actual data. The data are much richer. If you look at a condition, there are a whole bunch of subjects sitting over here in the subject pool that are allocated. They each give an initial judgment. Each one then follows, is allocated to a particular condition whereupon they give a further 2 probability judgments. Obviously, not all subjects can follow all paths because there's a conflict. The subject cannot hear both a weak prosecution followed by, in the same case, followed by a weak defense and a strong defense, unless the experiment is changed. The point here is that there are distributions across all the subjects for each of these 12 conditions. And those distributions are available. They're not available in the literature because they've never been reported, but they are available, and they've been collapsed in each case to a single average number. What does quantum cognition say about those distributions? So that's my first question.
Can we answer these?
Yeah, online, sure.
One at a time, because it might get. I don't know if Jennifer, you want to go first?
Well, I think the model that we developed is a simple model. And this model can be extended to produce distribution.
Why didn't you do it?
We have to start, I mean, this is incremental work. So we start and we want to look at,
Why did you choose an average and not a median? Why did you choose not the 10th percentile rather than the 70th?
this is a standard in the decision-making literature, is
Nice.
to take a mean. So why would we deviate from a standard practice?
Because you want to explain the data that you have.
No, because they were using the simplest concrete example, wanted to look for that and then generalize. I thought that's what we're supposed to be doing.
Okay, well, can I give an answer too?
Yeah.
So our work, Jennifer's paper, by the way, fortunately, fortunately you weren't one of the reviewers. You had to do all this work, but this was a simple shortcut for this paper. But in its simple, we want to start out simple. So this is our first simple step.
May I suggest that when we answer, because this is a discussion, turn around so we can all
Yeah.
hear.
So should we start out simple, because we don't want to start like, on the first papers with all these new ideas with a really complex analysis. But we have done subsequently with data sets, like I have a data set on decision making, a dynamic consistency experiment that was done with 100 subjects. Each subject made, about several, maybe 100 choices in this experiment. Each choice was a sequence of choices within a dynamic decision task. And so we have compared a quantum model on all the data. I mean, every single response made by every single subject in sequence in every trial, in the actual time series sequence. We've compared a quantum model to a traditional prospect theory model using a Bayes factor to compare the models.
Which quantum model did you use?
We use the same model that Jennifer uses here. Basically the same model.
Yeah, it's roughly the same.
Which one?
It's
Which
a paper.
quantum model?
Which model? Well, we developed a model. Actually, this model that Jennifer's using was originally developed by Emmanuel Potters and I, and published in the Proceedings of the Royal Society. In that paper, we developed Hamiltonian. In that case, the model was for a prisoner dilemma task where you had an opponent making a decision. You had to make a decision about what you wanted to do, and you had to make an inference about what your opponent was going to do.
Which statistics did you follow?
What?
Which statistics? Like Gauss or Fermi statistics?
Well, I mean, in the original paper, we developed this model, this Emmanuel Potters and I. And then we used the same model. The same Hamiltonian was used by Jennifer, and the same Hamiltonian was used by me in this dynamic consistency study. This dynamic consistency study was published by Rachel Barkhan and I in Journal of Behavioral Decision Making in I think 2003 or something like that. So we used this data set from that study. And in that original paper, we just tested a prospect theory model versus another model. But then we took that best fitting prospect model and compared it to this quantum model. Anyway, we compared our quantum model to the prospect theory model on all the data using a Bayes factor. And the Bayes factor, I was scared when I did this analysis actually. The Bayes factor overwhelmingly supported the quantum model. I mean, when I did this analysis, I thought, well, Schifrin told me to do this. And he said, well, quantum model, maybe it works better because it's complex. After all, it uses complex numbers. So I was scared. I mean, I was literally scared when I did this analysis, but the Bayes factor overwhelmingly supported. I mean, the Bayes factor, I computed the Bayes factor for each person. The Bayes factor for each person wasn't overwhelming. The Bayes factor for each person was on the average about 2, but I had 100 people, and they're all independent. So the overall Bayes factor across the experiment was huge. I think Michael Lee was in the talk one time presenting this. Do you remember that? Atlanta.
My head jerked up when you said all people are independent.
Yeah, right.
Don't you think people are I mean, they're independent choices. By independent people. I mean, we don't assume the choices are independent, we assume the people are independent. So, I mean, it was the initial study, we started out simple with means, but we haven't stayed there.
But I guess what Jeff may have in mind is the fact that the output at each of these levels is actually a random variable.
Yeah,
Yeah, no, that's a good, I mean, that's another point.
over a
Yeah,
population.
That's a good point, so that's something.
So in physical terms, you've got
Yeah, I agree.
a mixture.
I agree. Well, let's say, so if we wanted to build a, so Jennifer's model is like an oversimplification of this data. If we wanted to build a better model, which is something we have to do, to count because a person's giving a confidence rating and you get a probability distribution across confidence ratings. So what we really need to do, instead of using, computing a probability from the quantum model and assuming that probability maps directly into a confidence rating, we need a confidence model where the basis, like let's say you have, she had an example where you had 12 confidence states.
Mhm.
I mean, the subject marked a number 1 through 12. So we would have to have a quantum model where you have 12 basis states, one for each one of those levels of confidence. And then we'd have to develop the Hamiltonian to describe the evolution of a person's confidence across this 12 confidence levels up to some point in time, and then look at the distribution of confidence ratings at some point in time. Now, if we also wanted to, in addition to compute response time distributions, then we have to have a stopping rule for our quantum model. So we haven't done all that. We are working right now on a quantum random walk model, which will do exactly that. So we've got a confidence model that's not just 12, but let's say 100 state level confidence model. And we're doing a quantum random walk that achieves the same thing as the traditional random walks or diffusion model, where we're drifting up and down the confidence scale, and we're measuring you at different points in time, so we can get your we can get a confidence at a particular point in time, but we can also get a choice in the time it takes to make a decision from this quantum random walk model. But we're still working on that. Also, David Navarro and Jan Foos, they have an alternative quantum random walk model, different from ours, and they're trying to do the same thing.
Can I ask you?
Let's move on to.
For you, a quantum state, it corresponds to what in your experiments?
In this quantum random walk model, the states would represent different levels of confidence. So you're in a traditional random walk model, you're moving up and down the confidence scale. You're diffusing up and down the confidence scale. Like in traditional random walk model, you accumulate evidence until your confidence gets high enough to hit a threshold. Well, we'd have a similar kind of idea. You have a series of basis states representing different levels of confidence, and you'd have this Schrodinger equation evolving your confidence wave across these states, and then you would be doing a measurement at intervals of time to measure this, whether or not the confidence has exceeded the criteria. This is actually, this is interesting. Sorry, Jeff, I know I'm taking time. Jeff, whether he likes it or not, was really an instigator and facilitator of all this quantum theory by being the reviewer of many of my papers and attacking them at times and criticizing them. But like I said at the beginning of my talk, if he doesn't kill me, he makes me stronger. So he was one of the reviewers of my first paper. In fact, he went into the details of that paper, worked out a complete example mathematically to figure out what the model would be doing. It was a simple one, you had a three-dimensional one. I have to appreciate Jeff's effort in this. You might not realize that he's really
I do
helped
try to understand. Let me move on and come to my second query, puzzlement. States are labeled, the states that are a description of the state of belief of a subject. These are each complex numbers. The vector is normalized by the sum of the absolute value squared equals 1, which is sort of, again, standard in quantum physics. And my question is, what do these labels mean? It's pretty easy for me to understand that a subject is asking themselves the what is the impact of evidence that they are hearing on an ultimate judgment of guilt or not guilty. But the pluses and the minuses I find a bit strange. The plus is described as evidence. It's a label that attaches to any evidence of any kind that indicates guilt. And the negative sign, likewise, attaches to any evidence that's interpreted as favoring not guilty. This is first, why not, since the only evidence that's ever presented that is condemning a subject is from the prosecution, and the only evidence that is favoring the not guilty verdict is coming from the defense, these labels are confounded with the labels D and P, completely confounded. So there would seem to be no harm in replacing plus by P and minus by D. But there is a problem, and the problem is as follows. In the model, the subject is imagined to be in some initial state from which the subject evolves according to a unitary transformation, which Jerry describes geometrically as a rotation of an initial basis into a basis that's relevant for either the prosecution or the defense. It's the prosecution viewpoint or the defense viewpoint. Okay, fine. So, if we label states this way, you're a subject, you've given your initial probability, and immediately you're told, here is the prosecution's case. Before a word is uttered, as a quantum mechanical cognitive being, you collapse. That's the rule of the game. That's not what happens in the account that's published. Rather, you don't collapse until you undergo this evolution, this mapping of one basis to another, after which you collapse. Both ideas, that's the difference between replacing these labels by pluses and minuses. Where do you collapse? If you collapse initially,
Well, I'm not understanding, what do you mean, like, in quantum theory, you collapse without knowing?
you're making a measurement.
But the quantum...
That's a pure, that is a pure
the
state,
experiment-
that is a pure
The
state.
experiment has to pick the basis. The experiment has to decide where to put the angle to test the spin.
Excuse me, but why
No,
did
no, no,
you
no,
change
no.
basis in your unitary transformation?
You have,
And why not stay with the same basis and just let the system to evolve?
The basis for making the decision, or
it's,
the measurement.
they have an active viewpoint. So their state of belief stays fixed, and the frame in which it's expressed, the basis, moves. You could also equivalently fix the frame and have the state of belief move, which is probably more in line with a lot of intuition. right?
I mean, it's,
We-
either way. It's the same.
They are geometrically, they're equivalent. But just the change of, these are pure states. They correspond in your own terms to orthogonal projection operators. They're Hermitian matrices. They have eigenvalues 0 or 1. You carry out a collapse. So for instance, going back to the original, plus, minus, if the evolution, if the prosecutor is the first, gives the first evidence that is heard, then you're sitting up here. At the end of this evolution that takes you from the initial state to the prosecutor state, you then collapse. And your state becomes of the form. Do we agree?
Yeah.
If I change to, so why did you collapse?
Because, well, let Jennifer come. This is really her model, not my model.
Yeah, so I want to back up a little bit because I think it doesn't even make sense to use the representation that you have here. So we may be simplifying assumption.
I believe I use your notation in your
So,
representation.
right, then you changed it. So we were talking about the probability of some hypothesis given two pieces of information, A and B. We made a simplifying assumption that each of these events, or random variables, is binary. So this can be the hypothesis, can be plus minus, A can be plus minus, B is plus minus essentially. This is the simplifying assumption we made in this model. So here in my notation, instead of writing plus minus for the hypotheses, I write guilt and innocent. Here I'm
Okay.
talking about evidence because A is from the prosecution. So, I mean, if you're a bad prosecutor, maybe you actually present evidence for innocence. And in this case, we
you
did not
have-
test that. in
you
our
have
experiment.
no examples of that,
So Mackenzie, Lee, and Chen,
right? So as far as your subjects know, when you describe to them what you consider their state of belief, they would have been unable to distinguish between plus and P and minus and B. They can't.
well, I disagree with you. I mean, I feel that, there have been experiments that have been run where the defense actually presents evidence for guilt. And, I mean, they don't mean to, but this is how it's interpreted. And you actually
But
get
that's not part of your experiment.
It's not, but it was part of that paper as well. So we were motivated by some of these ideas. So when we were developing the model, we started with an idea. If I want a very simple model, and I'm starting from ideas in classical probability theory, I might have something that would be an 8-dimensional sample space, where I'm looking at all possible elementary events of the form, the intersection of H, A, and B.
In the solution, you have a mixture of states.
Right, so what we're thinking is that really the A and B, these pieces of evidence, are incompatible with each other so that they're treated as you have the state of belief and which changes and evolves based on the information that you're seeing. So this is just shifts in perspective based on different points of view. And that's why we use this sort of belief state to say, well, we're assuming that you can think about maybe the hypothesis and one of the pieces of information, and you have a way to form a compatible representation of this information which then evolves.
Well, excuse my confusion, but the language that you use in the paper when you talk about evolution is that you are rotating an initial frame of reference, an initial basis, to either a prosecution basis or a defense point of view. You don't talk about plus point of view and minus point of view. You
These
talk
are
about
outcomes for some random variable A. whereas A is prosecution, and these are possible outcomes. So a prosecution can present positive or negative evidence. We typically think that a prosecution is going to present evidence for guilt. But it could be the case that this is
I'm a bit confused by the notation. If this is a condition of probability, A and B, the order of A and B doesn't matter.
it doesn't matter in classical probability.
Yes.
And that's the whole issue. So we
Yeah,
said the
yeah.
classical model, it can't handle this. So this is why we're now looking at the probability that hypothesis given A, and we're transforming and projecting based on the information that we're getting for A, and then evolving for B, because this model doesn't work. A and B commute here.
Yeah, but you can make it work by collapsing A, B and make it one event, right? And then it's just one
So
thing, right?
AB
But they
is
have to
different
make a
from
judgment.
BA.
They have to
Yeah.
make a judgment at each point. So that in this particular experiment, that event doesn't, I mean, you have to have the separate events according to the experimental design.
They first see A and make a judgment, then
And
they
then
see A
they're
and
gonna
B and
see-
make a judgment.
Right.
Well, if these labels are not proxies for P and D, why are you collapsing? But that, oh,
Well, we're collapsing on the outcome that we get. So, I mean, if the prosecution is presenting positive evidence, then we're projecting onto that positive evidence subspace.
but in your account, this is inevitable. It's like,
It's inevitable in the fact that
Well,
we designed the
they use-
experiment.
Well, no,
so-
because if the prosecution presented evidence and the probability went down, you'd have to go to the negative coordinate, because the negative coordinate would lower the probability. The probabilities have to
Right.
sum up to 1.
So in this,
I mean, the amplitudes are not going to, the squared lengths of the amplitudes will sum up to 1. So they have to be, you know, if one is large, the other ones have to be small. And so if you're presenting if a prosecutor presents evidence that, sorry for the prosecutor, but the witness interprets it as evidence for the defendant rather than against the defendant.
but
Which
this,
happened in McKenzie's
this simply
case.
does not happen.
It happened in McKenzie's.
It
That's
happened.
what we started, that was the
that's,
main
that was
result
the
we started
motivation,
with.
and we actually tried to replicate that, and we couldn't get that effect.
McKenzie found that result. That's what we started with.
Let's, we can talk some more
That
about
was
this.
the original
Let-
experiment.
Let me
McKenzie had.
very briefly suggest, because I found this to be a bit of a can of worms. So here's a question. Why not simply have a two-dimensional vector, guilt, not guilty, and have all evidence act as operators? You can play your game directly on this two-dimensional object without difficulty and considerable simplification.
That's possible. I mean, you might develop a better theory than us. I'd be
I-
happy to have it.
Well,
Yeah, I'd like to see that model. Like, I mean, I don't think this model is.
you have SU2 acting.
Yeah, but we want to do this without many parameters, too. She's only got one parameter. The Hamiltonians all defined ahead of time. The only parameter we have in the Hamiltonians is what you correspond to the
Okay.
amount of rotation in time. So I think if you build.
If you want to pursue this, by the way, you can adopt a projective model in which the ratio, these are complex numbers, so this is very schematic, in which you are acting
Okay, well, here's one issue.
in a single complex plane
It might be a good idea.
and lose nothing.
And we may need to work on it. But one thing I worry about when you work in a two-dimensional space is then you have your subspaces of guilt is a ray. And so like the subspace of guilt is a ray, and you have guilt after the prosecutor, let's say guilt after after the prosecutor, then guilt after the defense. And if you look at that transition matrix, probably saying guilty after prosecutor, given, you say guilty after defense, or guilty after prosecutor, given.
They're different operators.
No, but you have a 2x2 transition matrix in your two-dimensional space. And that 2x2 transition matrix has to be doubly stochastic in the two-dimensional space. It doesn't have to be in a four-dimensional. We don't generally find double stochasticity. So that indicates you need either the quantum model's wrong or you need a higher dimensional space. So the trouble with working in two-dimensional spaces is you run into the problem of double stochasticity, which often fails. The transitions are not doubly stochastic.
That's a photon. Or let's take a spin half particle.
Yeah.
That's an electron.
Yeah.
There's no problem.
It has to be doubly stochastic. Of course, they find double stochastic. It does satisfy double stochasticity. So they don't have the problem in physics.
All right, let's look at your Hamiltonian, okay? There was a call for it. Here it is. Now, you are much better than I in explaining how these numbers come about. Let me put that aside and say, what would a physicist do when you say, hey, I've got this really neat quantum theory of cognition, and it's based on a Hamiltonian, and I'm going to be dealing with unitary operators generated by that Hamiltonian. And there's the Hamiltonian. It obeys a Schrödinger equation. The evolution obeys a Schrödinger equation. The first thing a physicist would do is diagonalize. You want to know, this is where the quanta come from. That's
Well,
the only place in your theory where quanta come from.
She did it in the appendix.
Yeah, and who asked?
Yeah, I don't know if you who's asked for that?
No, it was me.
Oh, I see.
You did nothing with it. You said, hey, you know, we got MATLAB, we can diagonalize. You did, but nothing happened. What did you notice about the eigenvalues? They came in pairs. And this is what a physicist would do immediately. It's unphysical. You've got negative energies.
No, you can add to
When
the
you
diagonal.
talk about the word,
doesn't change
when you
anything.
talk about a Hamiltonian
Yeah, but
you
I talked to
generating
you about
an
this before.
evolution, yeah?
You can add any arbitrary constant to the diagonal. And it's not going to change any of the predictions. It gets factored out. You can add an arbitrary constant to the diagonal. It changes nothing.
Arbitrary constant
Yes, it
here?
doesn't change anything. I showed
It
you.
certainly
You-
does.
No, you pointed this out in my 2006 paper.
No.
And I showed you a proof that you can factor the whole thing out. Yes.
This has to be traceless
No.
in
You can-
order for the
that you can take the
in
Hamilton.
order for the determinant of the
I
unitary
don't know.
matrix to be
I'm a little
one.
bit tired to do the proof right now, but you can show it's a. I have to download my 2006 paper, so it's a one-line proof. You can add a constant to this diagonal. It doesn't do anything to the probabilities. It gets factored out. It's a common phase factor that comes out,
I'm
and
not,
it doesn't have any effect
I'm
on
not
probabilities.
computing probabilities here. I'm saying, what are the stationary states, the states that stay
In
put
quantum theory,
as
the
you
diagonals,
evolve?
in quantum theory, the
And in
diagonal,
your theory.
in quantum theory, they always set the diagonal so the minimum energy is 0. Well, that's an arbitrary setting that they
No,
pick.
that's not so.
They pick it so it never goes below 0 because they designed it, the minimum is 0. But you can add an arbitrary constant to it.
Jerry.
Like, just add it like here.
This,
C times I.
yeah,
And then we work through that equation.
Yeah.
It factors out.
what do you mean it factors?
It factors out when you compute the probability.
It's not a unitary matrix anymore.
It is a unitary matrix. It's still unitary.
No.
Yes, it is. Because this is still, if you add a constant to this, this is still Hamiltonian.
The determinant of the matrix U
We don't have determinant is never zero.
The determinant of that matrix is the exponential of minus ix trace h.
I know. and
If
our
trace
determinant-
h is not 0, it's not a unitary matrix. Because the determinant's not
Determinants
like.
give you the product of the eigenvalues. We never had the eigenvalues
These
all
are-
zero.
Um,
These are not the numbers we have. But our
That's
eigenvalues,
your
our eigenvalues are never zero.
matrix. I've not said they're eigen. Here are the eigenvalues.
Yeah, so
They come in pairs of opposite,
the trace is going to
equal
be
and
the,
opposite
the
signs,
trace is going to be the sum of the eigenvalues.
correct? 2, minus 2, 0, 0, not the eigenvalues,
Yeah,
the
but that's
diagonals,
what's-
0.
all right, so
The
what-
sum of these
Yeah, but what are
is
we talking
0.
about the trace for anyway?
To ensure that that is
No,
unitary.
what you need for unitary, the only thing you need for unitary is this.
Take determinants. Come on. The
Well,
determinant must be of
I-
absolute value 1. It's either plus 1 or minus 1. We can ask why you eliminated reflections, which carry determinant minus 1, but that's another story. Your unitary matrices all have determinant 1. Your Hermitian matrices
Yes,
that you call
determinant plus 1, minus
Hamiltonian must have trace 0.
wait a minute.
Must.
He's correct on that.
Yeah, so I don't think our, but let's see now. But no, because the matrix, we checked it, it's unitary.
Yeah, I'm
Oh,
not
we checked
arguing
our-
with that.
We checked our matrix, it's unitary.
This matrix, which is your matrix, has trace 0. It is perfectly fine. But it has, if there's a physical analog of
No, but you can- what I'm
the
saying-
words that you use, Hamiltonian, Schrödinger equation, evolution, according to Schrödinger equation, the physicists would say it's unphysical because you've got negative energies.
Yeah, but you can, well, here's the thing. Okay, I have to sort all this out just a second.
It's a verbal
But you-
issue.
Yeah, but
It's not a Hamiltonian,
when we compute the probability,
you know?
you can add C times I here, and when you compute the probability, this thing will go factors out. and has no effect on the
Let's worry about that. It's a technical issue. The point is, this is not,
So we could add, if we wanted to, we could add a constant to this diagonal. It's
Yeah.
not gonna change our predictions at all.
you will destroy the unitarity if
No,
that.
because if you add a constant to the diagonal, it's not gonna destroy the unitarity.
Okay.
This is still unitary, because this thing right here, H plus Ci is still Hamiltonian. And as long as this matrix is Hamiltonian, this is gonna be unitary. The only thing you need for unitary is a Hamiltonian matrix. As long as, I can add anything I want to this diagonal, it's still unitary. The answer that you get out of this Hamiltonian will be unitary.
Let me just explain to everyone. A couple people are looking at me saying, how am I allowing this
Yeah.
to continue? The reason is that this is fairly fundamental to some of the things that are going on. But I think we should.
Yeah,
perhaps
let's-
Moving on to another topic.
Let me move on.
Question 5?
The evolution of states,
Oh, I see the problem here, because you took. This argument is on the unitary, this is the Hamiltonian. That's the problem you're having. I mean, yeah, you sum this up, this is 0, this is the Hamiltonian, but you can add anything you want to this, to the constant, and it doesn't change, it's still unitary, but you're gonna have a unitary now that's, the unitary is not gonna have trace 0, just because the Hamiltonian
I didn't
has
say
trace
it
0.
would, I said it had
Well,
determinant
so
0.
this trace of this
Determinant
Hamiltonian,
1.
so this trace, the trace, okay, the trace of the Hamiltonian is not going to be the trace of the unitary, because you have to exponentiate the.
I'm not
these are the
confounding them, I'm saying
These are
that
the
the-
eigenvalues of the Hamiltonian.
Jerry,
These are not the eigenvalues of the unitary. The eigenvalues of the unitary are exponentials of that.
correct.
So that's going to sum up the non-zero value.
What's question 4?
Okay.
So basically, he's got two things mixed up here. This thing factors out, has no effect. You can add this to the diagonals, and the unitary is not going to be 0 because we're going to exponentiate these eigenvalues.
I think this is something we're over a piece of paper. and
Yeah,
make it
this is a-
Probably a beer. I guess it's a question for Warren.
Let's move on to a related but quite different question. What is, and I asked this yesterday, this is the parameter, or it generates the 4 parameters in your theory, and there are 4 numbers, and they're labeled with the various conditions, and you have a real number, x, corresponding to a strong prosecution. You have 1 for a weak prosecution. You have 1 for a strong defense, and finally 1 for a weak defense. And they're the 4 numbers that constitute your parameter space, and you search the parameter space to find as good a fit as you can to the observed data. So explaining altogether 12 numbers with 4 parameters, right? Yeah, okay. What is the interpretation of the x's? Well, in physics, there's no question. It's a temporal variable scaled by Planck's constant. And it's a, I mean, that's critical. And the appearance of Planck's constant is no accident. There's nothing analogous here. Whatever constants there may be, you will have absorbed fine into the parameter. But how do I picture this evolution? So I start off with some initial frame, and it gets rotated according to this unitary mapping. And it ends, let's say I'm in a strong prosecutor phase. It will end as determined by that number. What happens in between? Do I go from this frame, suddenly jump to that frame? Or is it a smooth transition, or you don't care? It's not clear.
Well, you have to ask Jennifer this question. It's her theory.
Okay.
I mean, I'll tell you my answer, but her answer first.
You have to change this.
Well, in particular, is there any reason to believe that this is a larger or smaller number? That is, as you go from, you keep prosecution fixed, but you go from strong to weak or weak to strong. Is there an order?
We don't get an order. So this is a future direction we need to explore, is really understanding these parameters, because as I mentioned yesterday, the parameter space, it's oscillatory. And so because of that, and in fact, you can have multiple parameters that will provide the same fit to the data. So now it's going back and saying, how do we...
Where in the paper does that appear?
Well...
It's a cognitive science paper, not
It's
a
a-
JMP paper.
I mean, this was an introductory paper. Like I said, I feel like this is a very important topic, and I think it's a very important question. And it's something that we need to explore in further detail, which we didn't do in that paper.
Okay, so just to explain, what Jennifer is saying is this. You start off with your belief vector with respect to some initial frame. It's sitting there. You compute a probability of whatever, probability of guilt, and that's done by an appropriate projection and sums of squared amplitudes. Okay. Now you begin your unitary mapping. So you can leave the vector alone and change the frame. So the frame is rotating. And you can at least do this on a computer smoothly, continuously. Okay? What happens to the same probability that you computed originally in the initial state, probability of guilt? It goes like this. It oscillates. It has to. The reason is you're operating with an element, a one-parameter subgroup of the group of unitary matrices in 4 complex dimensions. It's a 15-parameter group. It's a big thing. It's been collapsed down to a 1-parameter orbit, and its action on the 4 vector, which has now been erased, but the 4 complex numbers. Think, and let's normalize it to 1. What does that look like? It's a bunch of angles. It looks like this. Cosine theta, sine theta, sine theta. I'm parameterizing the belief vector. Cosine phi, sine phi. Cosine phi prime, sine phi prime. And then you can chuck in any phases you like. Like that. Take the absolute values, square them, add it up, you get 1. That's the manifold on which this operator is acting.
So you are in a block sphere acting?
Say again?
Are you acting in a block sphere?
Is it
Block sphere is in two dimensions
Yeah,
here.
you can have
It's
also-
sort of, yeah. So you're wandering around this manifold, okay? And I've got to ask Don, how do we really picture this? This is not a simple thing. Angles, look, just think of probability of guilt. So when if you collapse onto the guilt subspace, you annihilate these 2 components, okay? Which gives you a cosine variation. And so you're varying an angle by acting on this transformation, and the cosine is just going up and down, okay? So if you think of x as capturing strength, and it's the only parameter in the theory that carries
Yeah, but
strength.
your concept of strength is coming from a class kind of...
No, I'm looking at your labels.
I know,
The
but-
only place
But
that
we don't
those...
assume they're monotonic.
Say again?
We're not assuming they're monotonic.
I'm pointing out very strongly they're not
Yeah, we
monotonic.
never did assume that.
We never did.
But this is what's giving you your multiple solutions.
I know it's giving you multiples. We'd have multiple solutions because it's not monotonic. We know that.
But what does it mean when you say the best fitting solution is,
What
and
happens
you give
is
a pair of values?
What happens, you start rotating close to, like, saying guilty, but then you rotate away, but then you rotate close and you rotate away.
But
And
does
you're rotating around it.
Is that in agreement with your intuition?
Well, that's the empirical question.
Oh.
That's not an intuitive question. In fact, I don't know if a Markov model, confidence always grows to an equilibrium and stays there.
Yeah, it's
But
highly
we don't-
interpretable.
Nobody knows that. So what if you looked at confidence and you saw some kind of oscillation around confidence across time? We don't know if it does that. Now, that's the empirical question.
Yeah,
point out some sort of psychology data showing actually the longer had stronger after actually can backfire, but sort of psychology data, like
Okay.
data. So it's possible to.
I will wager you $10, okay? That in this experiment, that would never happen.
Okay,
know.
but in
No,
this experiment,
you-
see, the thing is,
You have,
with Jeff, but what you're saying is how much movement is going to happen with each piece of evidence.
yeah,
And let's say guilt is here, and your state's, you got a guilt subspace here, and your state's here. The first piece of evidence might be really strong in bringing you up to this point. The second piece of evidence might bring you a little bit closer. Third piece of evidence might get you closer. You might get some law of diminishing returns and it just gets closer and never even crosses over. I mean, if it was the same step each time, it's going to cross over, but it's not guaranteed to be the same step because this is the amount of evidence. And this is the subject's interpretation of how much more evidence it is.
Jerry, you have to be able to get to any frame you want because you have a unitary matrix that will
but
do it for you.
You can pass it. If you have equal steps, you can pass it over. But if the person's taking steps and then the steps are getting smaller, you can converge on that point without passing because these x's are getting smaller. As each new piece of evidence, the first one might be large and move you a lot of the way. The second one might be smaller. The clock is slowing down.
I have no problem with
The clock
that.
is slowing down.
It is, but your explanation is not the one we want.
Well, you know, why it's not a matter of what we want. It's what
Your explanation has to explain, other than this object acting on that manifold is going to produce, by its very nature, it's going to produce oscillatory behavior. Okay, we understand that.
It gets close to the gilt space, and moves away a little bit.
Oh.
It oscillates around it. No, I've calculated it.
Yeah, me too.
Okay.
You're not damping the oscillation.
No, we're not dampening it. You can damp it.
But does it
something we haven't
seem-
included in quantum theory.
Jerry,
is
does
de-
it
is
seem
decom-
reasonable to you,
No, wait a
as
minute, wait a
you
minute.
add further and further evidence, more and more damning evidence, that your probability is going up and down and up
all right.
and down? Does that
It's-
seem plausible?
I've looked at, you can get confidence it damps up. No, it doesn't damp. It oscillates up and down
Yeah.
around the high level. But it doesn't.
The depth of the oscillation is pretty big. It's a
And
0.4,
if you want
0.5.
if you want to damp it out, we can, because we can add quantum noise that'll damp it out. You'll get decoherence and it'll reach an asymptote and stay there. And that's modern quantum measurement theory. They have quantum noise operators. That's what Ian Foose and Dan Navarro are using to damp it out. And so that's
Okay, let me
decoherence occurs
one last
by damping
question.
it out.
One last question. We all agree that the most elaborate feature of this whole theory is all about the construction and implementation of these changes of viewpoint, these unitary matrices, right? That's the complexity. That's why some people ask, hey, can I see this Hamiltonian thing, right? That doesn't explain order effects.
What we do is we compare two models.
No.
We compare
It
her model against
doesn't
another model.
generate order effects.
It generated with her parameters.
The only mechanism in your theory that generates
Well, you have to
order
have the
effects.
measurement too, of course.
It's
That's
the
the measurement.
projection and the rotation.
Yes, we have to have the measurement as well.
That's the only thing that generates the order
Of course,
effect
we have
is
to-
this collapse.
Yes, of course, we know that, yes.
Well, I've already argued that it's sort of hard to understand why you're collapsing at this particular point rather than that one, if at all. And the reason it's hard to, Jerry, please. Reason it's hard to understand is that you are giving, and this is where you really depart from physics dramatically, you are giving subjects access to at least the absolute value of their belief state.
Yeah, okay, yeah.
Why then would a subject have any need to collapse? They know the probabilities. They can read them off any time you want.
No, they don't know what her evidence is going to be. They collapse on the evidence provided by.
They can.
They don't know what the prosecutor is going to present. So the prosecutor presents something. Now they know what the prosecutor presented.
Yeah.
That's what causes the collapse. They got information, just like in a Bayesian model.
Yeah.
If you get information, you reduce, you conditionalize.
But-
So we're conditionalizing just like a Bayesian model.
But they are asked to make a judgment of guilt, and they're reading off their amplitudes. Why can't you ask?
They make the judgment of guilt after the prosecutor presents the evidence.
Okay, the prosecutor has presented the evidence,
But they
and
wrote
just before they collapse, they're looking, because these guys go away, they're looking at this state. And they can tell you every number, right?
I don't know about that. You're making up your own psychological theory now.
No. You're asking them to give you this number and that number, for example.
After the prosecutor presented information.
Fine. But in the meantime, as the evidence has been accumulated, this variable is changing, and it's changing smoothly. You can interrupt them at any stage and say, give me any one of these numbers. What's the probability that the person will be judged guilty despite evidence to the contrary? It's part of that.
If you could add, like, in other words, between the neutral person and before the prosecutor presents evidence, you could ask them, what's the probability of guilt? Like we do at the very beginning.
Why can't
and
you
you should
ask
get the
them,
same answer.
What's the probability of guilt given that you believe the evidence was favored innocent? Because that's part of this.
Yeah,
That's part of their state of belief. And you have given them the ability to read off those numbers.
Jennifer, do you want to make a comment on there?
Well, I
Talk
feel
about
like-
your stuff.
Well, I feel like we could have designed an experiment to do this. We just didn't ask those questions.
Okay, well,
Well,
I mean,
I-
this, let me put it
You
this
know,
way.
I mean, I can
In
only,
the Bayesian model,
I can
a
only
person-
react
and
to
Jeff,
what you
Jeff, in a
say,
Bayesian model, a person would
and
have to
I'm
have
reacting to your theory, which
Jeff.
generalizes beyond experiments.
But any
Can I say something?
probability model is going to generalize.
A Bayesian model
yeah.
would have to have some kind of, a person has to know what's the likelihood of guilt given this evidence? What's the likelihood of guilt given this evidence? They have to have that, we have to know the other way around. What's the likelihood of this evidence given guilty? You'd have a whole range of evidence. What's the likelihood of this different kinds of evidence given guilt? What's the likelihood of different kinds of evidence given innocence? And so you'd have, instead of having just two values, you could have a whole range of values. So we use 2 for simplicity. So the person doesn't know what the evidence is going to be. There's 2 possible values. But 2 is simplification. It could have been 100 possible values, but then it makes them all more complicated. So we pick 2 to keep it as simple as possible. It could have been 5 levels. The person doesn't know what the evidence is going to be. So if you ask them, what's the probability of guilt given positive evidence? Well, they have to know what they have some idea of the likelihood of the evidence given guilty. They have to have this information in the Bayesian model. They have to have the same information in the quantum model.
Let me suggest that what we have is questions have been raised and argued on both sides. I don't think we're going to solve it today, but I definitely think that these are issues that have to be seriously thought through, and perhaps in correspondence or later they can be handled. You got any others, Jeff, that you want to do this?
Let's either open up for general
Well, I think
discussion
we'll
or
open
call
up
it
for
quits.
general
Can I just say
Sure, go
something?
ahead.
I had to sneak one last little thing in, John. Anyway, by the way, this is not what we're not interested in summing these because we have to sum the diagonals of this. And the diagonals of this are going to be exponentials of these, but that's not the point. The point is, I really do have to say I appreciate, even though Jeff has been like giving me lots of headaches since 2006, like I said, he's been like pushing us to make this theory better. So
Well,
even all
remember my
these
background.
all these criticisms, will make us go back and work harder and
Well,
come out with better
that's
answers.
pretty much what I'm saying. is
Yeah.
You raised 6 questions, and they're partial answers, but it's clearly that the answers are not going to be found today.
I think
It's
a lot
clear
of
that
these
the
questions
answers
are really
going to have to be
important.
found when you get back to the lab or back.
A lot of these
home.
questions are really important. We don't have all the answers because it's a new field.
That's right.
And so we're working on it.
Thank you, Jeff.